Hello, everybody, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be talking a little bit more about plate tectonics. So we introduced the layers of the Earth last time. So now let's talk actually about the plates themselves. So here is a flat map of the plate boundaries. And again, these are the major ones. The Earth is split into hundreds of plates, right? But there are about 15 major slash minor plates. You do not need to memorize any of them. They will always be represented on a map in some way, shape, or form. But keep in mind that there are way more than these 15. These are just, again, a useful number of plates right now to utilize in order to explain a lot of the very broad earth science related things that we're going to be talking about in this unit. So these plates are situated on top of the mantle. Okay, the upper mantle is called the asthenosphere, and they are literally floating on top of dense liquid rock. So all of that, lava, um, the magma that shoots out of a volcano and then, it runs down the side as lava, that is what the continental and oceanic uh, crust plates are floating on, is very dense liquid rock. And the plates are in constant motion because of convection currents in the mantle. So in case you forgot from, like eighth grade science class, convection is the movement of heat in a fluid where hot liquid or gas rises and cool liquid or gas falls. We're focusing on the liquid aspect, obviously, because we're talking about convection in the earth. So here is a good kind of animation. You can see that the red little circle, like you can barely see it probably. In fact, on the slide, you might not even be able to. There is a very, very thin red line around the outside. That would be the crust. And then you can see the mantle actually getting heated by the crust, even though, sorry, getting heated by the core, even though the core isn't visible. It's just this giant, kind of black circle. But you can see that it is way hotter when in the mantle that is in contact with the outer core, and that is rising up. And then when it hits the cool crust, it starts to fall, and we get these cool patterns like that. I always say, if you've ever seen a lava lamp, kind of the rising and falling aspect of it, that is what convection is. And so the convection is caused by the heat difference between the really, really hot core and the, by comparison, very cool crust. And so we get this convection current of spiraling little motion underneath the surface of our crust. Okay, and that's in the mantle itself. Now keep in mind that this motion of the plates, because the plate boundaries are irregular little cracked edges, the plates are always constantly colliding with each other and separating. And when they do collide, there's a winner and a loser normally. And so the winner stays on top and the loser kind of gets pushed down into the mantle and starts to melt. So there are many, even though the earth seems as if it is just, this solid ball of rock, it is definitely not. So there are three major types of plate boundaries, and those are places where plates interact. The most common one that probably you've heard of are divergent plate boundaries. Divergent meaning separating, right? So that would be this. You have your, plates on top, the asthenosphere is under here. There are convection currents that are spiraling, and they are causing the plate boundary to separate. So these plates are physically moving away from each other. Here's a cool animation. You can see that, like, again, new crust is being generated as the plate boundary goes apart from itself, because magma or lava is spilling out at the top here, and so that's manufacturing new land. Good examples of where this is happening. So we've got the Atlantic Ocean and Iceland. So you can see right here, this is, well, I guess I should just say over here is the Atlantic Ocean, obviously. And this gigantic trench that you see is a divergent plate boundary. And so the continent of North America and the continent of Europe are getting further apart from each other. Right here, it looks like it's been cleaved in two, and it kind of has. This is Iceland. And there is a gigantic divergent plate boundary that runs right through the middle of the country, basically. You can see, again, some divergent breakage here in the ground. Opposite of a divergent plate boundary, another one that's pretty common that most people have heard of, convergent plate boundaries, right? So these are where plates collide with each other, and usually we have a winner and a loser. So we get something like this. Uh, you get the one plate is going to be moving into the asthenosphere, which again is the upper mantle, and it's going to start to melt as a result, whereas this one is going to basically get pushed on top of it. And so again, there are plenty of good examples of this, but you can kind of see this here where we have like a plate that's moving down into the asthenosphere, whereas now we have like this little lip is getting pushed over the top of it. So a good example of a convergent plate boundary, we have the Himalayan mountains. It's two continental plates colliding, so there isn't really a loser in that situation. Instead, they both just kind of get crunched together, and you get, where Mount Everest is right there. That's a convergent plate boundary. Um, Again, though, keep in mind that oceanic plates, can also collide with one another. The Alaskan Peninsula, there are two oceanic plates that are colliding together there. That's usually where you get winners and losers. Okay. And so we have a whole string of volcanoes and volcanic activity along the Alaskan Peninsula, mostly caused by that. Another great one, is the Andean Mountains. That's an oceanic and a continental plate colliding. And so in that situation, you end up with mountain range forming, right? And also normally because of the melting part here, because there is a losing plate, you get a ton of volcanoes that are also found along that ridge. All right. Next, we have transform plate boundaries, plates that slide horizontally past each other or laterally, right? So you get these plates that are scraping along the side. This is probably one of the least popular ones. We're in California though, so it is super important to us, the San Andreas Fault Line, right, in California. The Dead Sea also has it. So here's the Arabian plate and the African plate. And you can see that there's basically a tangential kind of movement along that. And that's going to be causing a transform plate boundary.